Hi, I'm Shuichi Hirahara from National Institute of Informatics. Today I'm going to talk about a new connection between average case hardness of NP and exponential worst case hardness. So the main result of this work is to prove the following theorem, which states that if UP requires the time complexity of 2 to the little order of n, then NP is hard on average. What's important about this result is that this has been a really long-standing open question, and there is a good reason why previously we haven't been able to prove this. The reason is that there are several proof techniques that shows a connection between worst-case complexity and average-case complexity, but these standard proof techniques can't be used to prove this result. For example, there are hardness amplification procedure and black box reductions techniques. These proof techniques can't be used to prove this result. Therefore, in order to prove this result, we needed to develop new proof techniques of analyzing average case complexity by using the meta-complexity. This is an overview of this talk. In order to explain the detail, I'm going to first explain the basics of average case complexity, and then I vary a result, and then I will explain our result, and I will mention some proof techniques. First of all, why should we study average case complexity? There are two main motivations. One is to understand the practical performance of algorithm. For example, let's consider the Hamiltonian path problem. It is known that it is NP-complete problem, which means that we can't solve it in the worst case in polynomial time. But if you consider a natural distribution on input, namely an L-linear random graph, you can actually solve it in expected linear time. Therefore, even if a problem is hard in the worst case, it doesn't mean that it is difficult on average. Another motivation is to understand the security of cryptographic primitives. There is an important cryptographic primitive called one-way function. And in order to build a one-way function, we first need to prove that NP is hard on average. So these two motivations are important motivation to study average case complexity. Now let me review the basics of average case complexity. In the theory of average case complexity, we are concerned with a distributional problem. A distribution problem is a pair of a decision problem L and a family of input distributions. Then we define an average case analog of NP as distributional NP. Distributional NP is a class of distributional problems L and D such that L is a problem in NP and D is a polynomial time sample distribution. In other words, we don't consider any distribution that can't be sampled in polynomial time. Instead, we focus on analyzing average case complexity with respect to polynomial time sampleable distributions. There is a notion of average case polynomial time, which is denoted by average p. We say that a distribution problem is in average p if there is an average case polynomial time algorithm A and a time bound t that satisfies the following three conditions. First, the algorithm must be correct on every input. Second, the algorithm runs in in time t of x for every x. Thirdly, we require that the algorithm A runs in average case polynomial time in the sense that the expectation of t of x is at most in a polynomial in n. In order to make the definition robust, we are allowed to choose some small constant epsilon in the exponent. So this is the notion of average case polynomial time, and actually this is known to be equivalent to the notion of errorless heuristic scheme. In this work, we also consider a stronger notion of p-computable average case polynomial time, which is denoted by average sub p, p. This is a stronger notion than average case polynomial time in the sense that in addition to the three conditions, we also require that the time bound is computable in polynomial time. Let me give one example about average case complexity. If you consider the Hamiltonian path problem with respect to L-linear random graph, you can show that it in average case polynomial time, but you can also show that average PP in the sense that there is a P computable average case polynomial time algorithm for Hamiltonian path problem. A big open question in the theory of average case complexity is to connect the worst case hardness of NP to average case hardness of NP. Specifically, if NP is different from P, can we prove that the distribution NP cannot be solved in average case polynomial time? This is a central open question, and this question is essentially equivalent to whether we can rule out heuristica from 5 possible worlds of Impagrazzo. Remember that heuristica is a hypothetical world where NP is hard in the worst case but easy on average. Excluding any world from Impagrazzo's 5 world is a central open question in the theory of computation. Currently, there is a much weaker open question. Even if we assume that UP requires exponential time complexity, we didn't know whether pH is hard on average. The reason why we haven't been able to resolve this question is that if you take any proof that proves this result, that proof must bypass 3 barriers simultaneously: impossibility of hardness amplification, limits of black box reduction, and relativization barriers. Before explaining the barrier result, let me quickly remind you about the several complexity classes. pH stands for polynomial time hierarchy, UP stands for unambiguous polynomial time, and one way to think about the UP is that the complexity of UP is related to inverting one-to-one function in the worst case. Now let me explain 3 barrier result. If we want to connect the worst case complexity and average case complexity, there is a quite general proof technique that is called hardness amplification procedure. A worst case hardness amplification procedure is a procedure that takes a Boolean function f and maps it to a hardness amplified version of f. And we have the following property. If f is worst case hard, then the hardness amplified version of f is average case hard. In other words, worst case hardness amplification procedure amplifies the worst case hardness of f to the average case hardness of amp to the f. And after a long line of research, it is now well known that there is a p-space computable hardness amplification procedure. This means that we can prove that the worst case complexity of p-space and average case complexity of p-space are equivalent to each other. Now, given these general proof techniques, it is natural to wonder whether we can use the same techniques to prove the frontier open question. Namely, can we establish the connection between the exponential time complexity of UP and average case complexity of pH by constructing some hardness amplification procedure? A natural way to do this is to make sure that the hardness amplified procedure is computable in pH. Unfortunately, a strong negative answer was given by Buehler. He gave 2 incomparable results about impossibility of hardness amplification, and the first result states that there is no hardness amplification procedure that is computable in pH. But there is some technical condition saying that the relationship between f and the hardness amplified version must be proved by black box reductions. Even if you don't have this technical condition, he proves that if we have a hardness amplification procedure in pH, then P is different from NP. So the message of these results is that it is very difficult to construct a hardness amplification procedure in pH. So we should consider a different approach. There is a different approach which is called black box reductions. Using a black box reduction, we can prove several connections between worst case complexity and average case complexity. For example, ITI showed that if the shortest vector problem is hard to approximate in the worst case, then NP is hard on average. We can also prove that SZK is hard in the worst case, then NP is hard on average. Similarly, by using a simpler padding argument, we can prove that if NP is not in 2 to the big O of n, then NP is hard on average. These results can be proved by black box reduction. What I mean by black box reduction is that a reduction makes several queries to an oracle, and an oracle is guaranteed to solve some distributional problem in NP, and given answers from oracle, the reduction must solve the problem in, for example, SDK. So the reason why this is black box is that we don't require any efficient requirement on the oracle. So the approach of black box reduction is quite useful because we can prove a lot of connection between average case complexity and worst case complexity. Now the natural question is that can we use similar proof techniques to prove the frontier open question? Unfortunately, a negative answer was given by Feigenbaum-Foltmann and Bogdan-Toropizin. They showed that there is no non-adaptive black box reduction that can show such a connection unless some complexity theoretic collapse happens. So the message of this result is that we need to use either non-black box reduction or adaptive reductions. In this work, I'm going to use non-black box reductions. There is yet another type of barriers, which is relativization barrier. Impagrazzo constructed an oracle under which UP requires the time complexity of 2 to the n to 0.1, but NP is easy on average. What this barrier means is that if you want to achieve the time bound of 2 to the n to 0.1, we need a non-relativizing proof techniques. Let me mention that our proof is actually non-relativizing because we rely on a previous result of Berman-Fulton problem, which doesn't seem to relativize. Now let me state our result and proof techniques. In this work, we were able to bypass all the three barriers, and we were able to prove the following three main results. First, if UP requires the time complexity of 2 to the order n by log n, then we can prove that NP is hard on average. Similarly, if pH is exponentially hard, then we can show that pH is hard on average. These two results resolve the frontier open question mentioned earlier. And note that if you consider the first item, any proof for this must overcome the barrier result of Biolo and Bogdanov and Toropizin, while our result is not subject to the barrier of Impagrazzo. For the third result, we can show that if NP requires exponential time complexity, then we can show that NP is hard on average, but it's for the stronger notion of P computable average case polynomial time. This excludes a weak variant of heuristica in the sense that our world is not a world where NP requires the time complexity of 2 to the order n by log n, and NP is easy on average in the sense of P computable average case polynomial time. Let me mention that you might wonder P computable average case polynomial time is strong notion, but actually we can prove that average PP and average P are equivalent for if you want to solve pH. Let me explain our proof strategy. Our proof is based on metacomplexity, which refers to complexity of complexity. There are several examples of metacomputation problems such as MCSP, MKTP, and MinKT. In this work, we are going to consider MinKT, which is a problem of computing the time-bounded Kolmogorov complexity. Let me recall the T time-bounded Kolmogorov complexity. The T time-bounded Kolmogorov complexity of a string x is denoted by k subfactorial T of x, and it is defined as the length of a shortest program that prints x in T steps. MinKT is a problem of deciding whether the KT complexity of x is at most s or not. We also consider a generalized version of min-kt, which is denoted by min-kt superscript a. This is a problem of computing the A oracle T time bounded column complexity of X, and A oracle time bounded column complexity is defined as the length of a shortest program that prints X in T steps, but the program is allowed to have an oracle access to A. Then min-kt to the A is a problem of computing the A oracle T time bounded column complexity. You might wonder that A should be reducible to min-kt to the A, but we don't know whether this is true. What we know for sure is that we can prove that min-kt to the A is a problem in NP to the A. Why should we consider a meta-complexity? The reason is that we can actually characterize average case complexity by meta-complexity. Last year, I was able to characterize the average case complexity of pH by the worst case meta-complexity of min-kt to the pH. We can show that pH is easy on average if and only if gap min-kt to the pH is easy in the worst case. This statement means that for every oracle A in pH, gap min-kt to the A is easy in the worst case. Gap min-kt to the A is an approximation version of min-kt to the A. What's important about this characterization is that as a corollary, we can get a new proof techniques of analyzing average case complexity by using the notion of meta-complexity. For example, we can get our average case hardness amplification result for pH as a corollary of the characterization. The statement itself isn't so important, but what's important is how this is proved. We can prove this statement by going through the notion of a worst case meta-complexity in this way. In this work, we follow a similar approach to analyze average case complexity. So the reason why this characterization is helpful for us is that in general, worst case complexity is easier to analyze than average case complexity. Now let me explain how we proved the connection from the exponential time worst case complexity of NP to average case complexity of pH. Actually, we are going to prove the contrapositive of this statement. And in order to prove that, we draw a similar diagram. Namely, we first go to the notion of worst case meta-complexity by using a previous work, and then we consider a new notion which we call a universal heuristic scheme. Before explaining the definition of a universal heuristic scheme, let me first explain a property of a universal heuristic scheme. The reason why we call it universal is that we have the following universality. For every problem L, we can show that the following two statements are equivalent. The first condition is that there is a universal heuristic scheme for L. The second statement says that L can be solved on average in the sense of P computable average case polynomial time with respect to every polynomial time sample distribution. So this universal heuristic scheme has a nice universal property. Let me explain the definition of a universal heuristic scheme. There is a beautiful notion of computational depth, which is denoted by CD superscript T of X. This is the difference between T time-bounded column complexity of X minus time-unbounded column complexity of X. In this work, we are going to generalize this slightly to TS time-bounded computational depth, which is simply defined as the difference between T time-bounded column complexity and S time-bounded column complexity of X. Now we can give the definition of a universal heuristic scheme. We say that an algorithm A is universal heuristic scheme for L if we have some polynomial P that satisfies the following two properties. First, the universal heuristic scheme takes input X as well as a time parameter T, and it must be correct on every input. Second, the running time of the universal heuristic scheme is at the most 2 to the order of t p of t computational depth of x plus log of t for all large t. This means that the running time of the universal heuristic scheme is characterized by the computational depth of x. This is the definition of a universal heuristic scheme. If we have a universal heuristic scheme, we can show that there is a worst-case algorithm running in time 2 to the order n by log n. Let me explain this in the next slide. In general, if there is some universal heuristic scheme for L, we can show that L can be solved in 2 to the order n by log n time. The proof idea is quite simple, so I can explain this. The main proof idea is to find a time-bound parameter t so that the input becomes computationally shallow in the sense that the computational depth is at most order n by log n. To show this, let's consider the following telescoping sum. We first consider t time-bounded computational depth of x, and next you consider p of t time-bounded computational depth, and so forth, and you repeat it I times. This is a telescoping sum, so what remains is that the first term and the last term. So we get this, and then we can bound this by n, basically n. So what this means is that we can have some index I such that the computational depth of x is at most n by log n. Remember that a universal heuristic scheme runs in time 2 to the order of computational depth. So by using this, we can consider the following natural algorithm B. This algorithm runs the universal heuristic scheme for several different parameters, t, p of t, and p square of t, and so forth in parallel, and you take the first one that holds and output what it outputs. The correctness of this algorithm is very simple because universal heuristic scheme is correct. If you want to measure the running time of this algorithm, we take the first one that holds. So we can take the minimum I of the running time of the universal heuristic scheme, which can be bounded by 2 to the order n by log n, which comes from this computational shallowness. So this completes the proof of this lemma. So we have explained this easy implication. In order to construct a universal heuristic scheme, we use the notion of direct block generator, and we also need a new technical lemma, which is called weak symmetry of information. And we can also use a direct block generator to prove this implication. So by combining these implications, we can prove the connection, the worst case to average case connection. Let me explain how we overcame limits of black box reduction. Let's assume that pH is easy on average, and let P of n be the running time of the average case polynomial time algorithm. Then by going through this implication, we can show that there is a universal heuristic scheme which runs in 2 to the order computational depth of x. But here we have some polynomial p prime, which depends on the original running time of average case polynomial time. In this sense, the reduction is non-black box because we exploit the efficiency of average case polynomial time. Therefore, our proof is not subject to the barrier of Bogdan-van-Trapezen. Let me also explain how we overcame Biola's barrier result. Actually, our result can be regarded as a Hardness amplification procedure in some sense, but there is some important difference. Our Hardness amplification procedure must be defined on all input lengths. On the other hand, Biola's proof techniques can be applied only if the Hardness amplification procedure is defined on a fixed input length, m. In other words, if we could extend it to all input lengths, by combining Biola's barrier result with ours, we would be able to resolve P versus NP. To conclude this talk, metacomplexity is a very powerful tool to analyze average case complexity But there are a lot of interesting open questions. Thank you for watching this video.